Starting, yes. Good morning, ladies and gentlemen. The very first thing, are there any questions? About the project and about the website. If you want to see this website, you should go to Sunlearn, where it lists Rekenaar Wetenskap 144, Computer Science 144. You should click on that link. If you find any other versions of the website, it's outdated. The Sunlearn one is updated with the correct test dates, for example. The other thing, you should please read email address to CS144. Yes, I always get complaints about that, but I'm old. What can I say? I work with email. So I send out messages about this course. So please read it. Yes? For example, confirmation of the test dates have been done. I sent out examples of input files for the project, and so on and so forth. Right? So I'm probably preaching to the converted, because if you're sitting here, you're one of the people who actually do read your email. But anyway, please do that. Then the other thing I need to say is that I hate assessments. Frankly, my idea is not that you sit in a course and you actually have to pass the course. My idea is that you sit in a course and you learn something. I would. Because you can actually pass without learning anything. Learning things that you can, that's of value to you. Yes? I'm not talking about memorizing. I'm talking about, I'm a richer person because now I know how to do these things. Yes. However, I'm in a system where I have to give assessments. So I try to make my assessments, set up my assessments in such a way that it will test whether you did learn something. Yeah. So the question becomes, how do you learn something? What are you supposed to learn up to now? In section 3.1, what the textbook tries to is to get you used to the idea of objects, but all they present is an API, and in 3.1 they then show you if you write what we call a test client, so if you write your own code, how do I use the API to, say, use complex numbers or make particles or things like that. So those are examples of using the API. Gesundheit. What you need to do in order to learn the required concepts is you look at the examples in the book and you ask yourself, well, what if I have something similar? What are they doing? What are the tricks? Why do they do it this way and not another way? In other words, I don't want you to read the book and memorize it. You might pass with a 50 or a 55 if you do that, but then you've learned nothing. So the only way to learn this, to get something out of this course, is to play with this stuff. So the moment you see an example, go to the computer, run this example, then look at it and say, I wonder why they did it this way and not that way. And then you change the code to do it that way. Sometimes it will also work. And then you know it was just a matter of convenience or notation or whatever. But sometimes it won't. And when it doesn't work, you have to figure out for yourself, why did it not work? Okay? And then also in 3.1, memory, 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 memory. How does the memory work? Because you have to understand this whole thing about references. Yes. So there are some neat little examples. Remember in 3.1, like this one, overwriting a reference instead of making a new copy of the object. So you have to get that one wrong. But I think we got it, sort of, mostly. I say it at least 10 times in each lecture. If you work with a variable name for an object, you are working with the reference, not with the values. Right. So section 3. Is different because in section 3.2, we assume you now know how objects work in memory, where and how are the objects stored, and how to use the objects in client code. Okay. Been there, done that, 3.1 finished. In 3.2, the idea is, well, how do I actually write that Java code that implements the constructor for a given abstract data type that I want to make, for a new data type that I want to make? How do I write the constructor, and how do I handle the instance methods there? And then the whole thing. And we had a bit of a discussion on Monday. Why do I make variables private? Yes. When do I make them final? Because this is a very strange concept. You're making an object, you're declaring instance variables, but you make them private final. So they get a value once, and that value never changes, which is really weird because up to now you had variables and the variables kept on changing their values. That's why they're called variables. Hulle verander gedurende hulle waardes. Hulle is veranderliks, right? But in object-oriented programming, you have to do a little bit of a mind switch. If I make a thing, and that thing has certain values, those values must not change. If I want other values, I make another thing, and then I have different values. So that's different from the way you've programmed up to now. And that is the difficult thing to handle for yourself when you have to write the code. That is the thing that you have to get your mind around. So in section 3.2, there is really only, mostly, no, not only, there is mostly lots and lots and lots of examples. And what you need to do is to work through the examples and ask yourself, why are they doing it this way? Yes. And all the little itsy-bitsy teeny thingies that can trip you up when you make your own objects. Okay? How does Java handle this? Why does it work this way and not that way? Yes. When do I make a thing final and when don't I make it final? What? How do I make objects? Because with objects, I send over variables. So now I'm very tempted to have instance methods with lots of variables, and so on and so forth. So the whole design issue about which instance methods must I have and so on, we'll do in section 3.3. But section 3.2 is deceptively easy because, oh, wow, okay, look at this cute little example, yabbity, 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 yap. Okay? But what you're supposed to do is to look at the style of the implementation. For every single line, ask yourself, how could I have done it differently? Why did they do it this way? Okay? So my very, very lame analogy is computer science is like riding a bicycle. I can stand here and explain it to you until I'm blue in the face, or green, but okay. Some or other non-natural color. But then you still won't be able to do it. Not until you climb on the bicycle and practice it. Right? So that's what the dots are for. Please, please, please use the demos. Ask them lots of questions. Okay. Yay, my sermon for the day. I should have been a preacher. Okay. Poor flock. Everybody would have become atheists. But okay. If I were a preacher. Right. But the advantage of all my preaching is that you will be so fed up with it that you will pass the course, otherwise you have to see me again next year. So, good. Yes. Right. So this is an example. I don't know if any of you have ever seen this sweet little programming language called Logo. That was about in the late 70s, early 80s. And the idea was that this is a programming language that you can use to teach primary school children to program. And you had a little picture of a turtle on the screen, and then you could give commands to it. And as you give the commands, the turtle moves and draws behind it. Okay? So, turtle graphics. And the nice thing about the turtle graphics is that we can make an object. Now look at this. I think about the API and I make a constructor, and the only thing that one needs to know about the turtle, something that can move on a screen and draw the line, make it a pen, make it a laser pointer, whatever, this is just called the turtle. You are at a certain position in the Cartesian plane, and you have a certain direction in which you are facing relative to the Cartesian plane, right? So that is a certain angle from the x-axis, yes? A0 is my angle, and I'm facing there. And what that is constructing that specific turtle. Now, what the turtle can do is simply the following. It can go forward a certain number of steps. I have to tell it how far to move. Yes, 1 step, 2 steps, 3 steps. Or it can turn left. And how far does it have to turn? A certain number of degrees. Okay, and that's it. And then you can write client code that can start using the turtle. For example, if I have a turtle, I can make it go forward. Yes, I can make, now it's there. The turtle started out here, it went forward a number of steps, it turns left 120 degrees, it goes forward again, it turns left 120 degrees, draw it right. Some more aggressive, so a few pages on my a number of drunken turtles, yes, because a turtle is an object. I'm not restricted to one turtle. I can make gazillions of them and let them all move. And what they're doing over here is they're not randomly. Remember you had the random walk thing in the first semester? So they're moving randomly and they're doing all sorts of interesting things. This is not a trivial example. Random walks are mathematically extremely interesting. And in the maths department, there's actually Stefan Wagner, does research. I would say combinatorics, but it isn't. Combinatorics, and he has had a number of master students working on random walks because you can model nature with random walks. You can model all sorts of processes with random walks. Okay? So the random walk idea is very interesting. And then from a programming point of view, this illustrates the use of objects. So I just need to convince you that you don't have to go through a lot of Java to draw a triangle, right? Because I could have done this by hand. Okay, so here is an implementation. We are in section 3.2. That means we are interested in what the code looks like for a turtle. How do I write the Java to make this object? I need a constructor. Why don't I have Mr. Wilson? Why don't I have static void there? Anybody else? Mr. January? Why is there not a static void there between public and turtle? This is not constructed. Sorry, yeah. Return value because this is a constructor, so I can't use void. Why can't I put static in there? That makes it a function. Excellently put. Good answer. I am writing instance methods. It's a difference when I do this. When I make objects, I use instance methods. Instance methods are the opposite of static methods. A static method simply implements a function. Calculate and send the value back, right? But this is an instance method, so I cannot have static there. Well, in the constructor, right? Normally, look at the constructor. I designed it to be the memo for I and puts in the first initial values. So what are the initial values? Well, the way I call the constructor. So the parameters go into X, Y, and angle. Note that those are not final. Whereas with good old charge, or with good old histogram, which you have to read on your own, here is charge. Over here, not find charge at a certain position. If I stick to that position, yes, I do not change my X or Y, I stick to that position, the charge stays the same. I have a turtle. It is currently at a position, but boy, am I going to move that drunken turtle around. Okay? That's why it's not final. Okay, implementing some of your instance method, I will not return simply turn. It will have a new angle. How does it work? I say by how much my current position must change. My current position, yes? and I add that value to a different angle. And now the turtle is turned in a different way. Now I can make it go forward, blah, 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 using radians and steps and maths and sin and cos and whatever. I can, if I want to go forward a number of steps, I must start at my current position and I must end up at a new position. Yes? So my angle doesn't change if I go forward, but I am at a new XY position. So therefore, I remember, yes, my current X and Y positions, and then I add to my current XY why you get all this nice trig functions. Yeah. Calculate position must be, you draw a line from the old position to as easy as possible. And here is a test. This one is very cute because you can draw a polygon with any number of sizes. This is what this little piece of client code does. It calculates how many sizes. So Java Turtle draw me a triangle. Java Turtle 7 will draw me a whatever you call a 7th thing. And if you make your sides, the number of sides large enough, you get a circle. Of course. Yes. Okay. This is also a very cute one. So let's look at this. Nothing stops me from making an object and then using that object in a recursive procedure, in a recursive fashion. Recursion is so nice. So, this thing, public class Koch, there is something called a Koch curve. Well, you call it a curve. It's a pattern. Yeah. They call it a curve. So a curve, which is just a flat line. And then what? One. Then you took off line to the second -1. Then you turn on right 120 degrees and you draw a third curve. Right? So here I am. Yes? I turn blah, 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 blah. Okay? And if I do this repeatedly, you can see that every straight line gets this little stays the step size is what I get, but I'm doing this in steps of 3. I have a straight line, a piece jutting out another piece, a piece, another piece, another piece. And each one recursively has 3 parts to it. Okay? So you can see this part looks exactly like that, just smaller, and so on and so forth. This, incidentally, is in graphics used to model snowflakes. Imagine when you look at this picture, you can already sort of see part of the snowflake if you use your imagination. Some of you are fairly interested in 3D graphics. Yes, I know you've done some extra work on 3D graphics last semester. The rest of you should have a fair idea of how graphics works. because you're computer scientists, so you should know how every computer application, you should have a rough idea of how every computer application works. Okay? Playing World of Warcraft, playing Star Citizen, playing, I don't know, what Ark Survival Evolved, okay. I have housemates who do play that, so I'm called to watch this nice thing every now and again, and then I go there and analyze the algorithms that do this out of the room. Because you know that in graphics, if you play graphics-intensive games, you have information that passes between the server and your computer, or you have to have a very nice graphics card on your computer to render this. So you have to generate things like landscapes. And some things are particularly difficult to realistically. For example, fire. It's a thing that's not so easy to do. So almost all the graphics that take place in all these rests on foundations of truly intricate mathematics. Okay? Things like fire can be generated by automata. So you have systems of automata, and they can do this recursively. Trees are quite difficult, which is a bummer because almost all the landscapes that you see in these online games have forests and forests of trees. And you do know that things in the far distance are not rendered completely. Things that are near to you in the computer rendered completely because sensitivities. And this is so a mountain in the background would literally just be the lines and color texture. And trees in the field because it's too expensive to render everything in detail. And just the things that are near to you would be rendered in detail. About 3 years ago, I examined a master's thesis from someone at UCT, and he was working on trees. So rendering trees more efficiently. You have to pass your maths. There's either a hell of a lot of calculus or a lot of formal automata theory to do good graphics. Right. Those are Koch curves. Incidentally, the number of steps in a curve of order n is 4 to the n. So how many steps must I do? Oh, is this linear, quadratic, or exponential then? Thank you. But what does it mean? If I tell you to generate this will take 4 to the n is exponential, yabbity, yabbity, yab. Do you know how fast it will run on the Narga computer? What is the largest that I can make n without having to get up, get a cup of tea, chat up somebody else, come get a date for next Saturday, and then maybe my Koch curve is finished? How large can I make n? What is 4 to the 10, roughly? What is 2 to the 10? That you must know. 1024. Therefore, 4 to the n is roughly 1,000 by 1,000. Oh my word! N is 10, which is so small. If somebody gives me 10 rand, I can't even go buy a coffee. Yes? depending on what you drink. I like expensive coffee. Okay. 10 is so small. Yes. But to generate a Koch curve with n equals 10, it will require over 1 million steps. Okay, 1 million is big. Now, if it's 11, if it's 12, but more important than that, how fast can I do this on a standard computer, roughly? Yes. How long will it take me? I'm working with Prof. Geldenhuis on a very nice greedy algorithm to find cycles in the path. And we are currently has been running for 148 and we haven't got our answer yet. On a nice fast server up in there. Yes. So you have to know, you have to have a gut feeling on the computer. What does it mean to make 1 million steps? Yes. And I can give you the minutes and it's 8:30 on a word. So please go to the computer, run Koch repeatedly for n equals 1, for n equals 2. I mean, it's so fast you can't even hit return before the answer is there. It gets a bit slower and a bit slower and a bit slower. So get a gut feeling for what the numbers can be. Okay? I really am. Okay. Poor little turtle. It had to make 4 to the end steps, and now it's very tired. So as you get tired, your steps get smaller. So if we change that Koch curve thingy that can draw the snowflakes to make the turtle take progressively smaller steps, what will happen? What you get? Spira mirabilis. Yes, a miraculous spiral. And you've all seen that. A Nautilus show, pictures of a galaxy, a storm. You saw there was a tornado yesterday in Joburg. Huh? You see that? So this is the inside of a tornado and so on. Okay. By simply changing the step size. Okay, all very interesting and amusing and so on. The point being over here, I made an object. I call an instance method. Once that code is correct, I can use this I to get quite different effects. Okay, right? Okay. So this is just the client program, and now let's drink a bit. So now I can up this lecture a bit. Brownian, yes. Okay. And incidentally, if you manage to continue up to your 3rd year, if you manage to continue up to your 3rd year with theoretical physics, there's also a computer physics module, which is great fun. Of course, and very easy for you because you've done computer science. Okay. With our turtle, remember that code has been implemented, it's been tested. I have a turtle. There are not any bugs anymore. Everything has been sorted out. And now I just write 5-line. Wat's met julle aan die gang? Kry julle koud dat julle lippe moet beweeg om warm te word of iets? Waar was ek nou? The only thing that I change is my 5-line client code and I get something totally different, right? So we want to do the following. To simulate Brownian motion. Okay, ons moet, kyk as julle verveeld is, moet julle loop. Okay, want anders gaan ek loop. Want dis ontsettend. Met Freak my heeltemal uit. Okay? So if you're bored, I never bother if anybody leaves the class. If you're bored, off-ski. If you're not, then don't talk all the time. Okay. So the only thing code is to the turtle is simply make it move, make it turn in a random direction. Yes, so I have my turtle, the same thing I used to draw that boring little triangle, yes. And the other is I change the direction. Instead of a fixed 60 degrees or 120 degrees, I make it turn a random number of angles. Okay? And then I get this, which is so cool. But please note this. I still have only one turtle. Yeah? So it's one turtle doing this stuff. Okay? Fixed distance. What I now want to do is improve on this. And now I declare an array of turtles. Okay? Please, 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 please. When you use objects in an array, you have to new. You have to new once to get your array. Yes, so now I get an array of turtles, just like I would have gotten. How I would have gotten an array of integers or something. Now I have an array. I have my reference to the array. Yes. I knew, so I get my memory spaces, and each space can contain the information for one turtle. Yes. But the values have not been filled in. I just knew for the array. So over here, in a loop, you have to new each individual turtle. Okay, so each individual object in the array has to be new. Okay, and now you go zonkers, and you have nice kids. Okay. Let's find an example which is slightly more scientific. You all that in math is a prerequisite for the subject. You did complex numbers, right? So a complex number is a number of the form x plus I, y, where I is the square root of -1. And we had to look at complex numbers. Let's make it an object because I'm going to do a lot of calculations for some other subject. And I need complex numbers. So instead of manipulating it by methods on my own, I am writing an object. Okay? I can plus, I can times, I can take the magnitude, I can take the real part, the imaginary part, and I can print it. So that's the API. I know what I want to be able to do with a complex number. Yes, I want to see what's the real part, see what's the imaginary part, I want to print it, therefore I have to have two string. I want to add two numbers, and I want to multiply the numbers. Okay, that's my API, and I know how it works. But if we get to the implementation, we need to look at the suggested implementation in the book. Firstly, I will make private variables, which are final, which is somewhat strange. Don't they want to change values? I mean, you give me an integer and I can't change the value. So now you give me a complex number and I can't change the value. It just has a value. So you have to think so much of complex number is there. So all the complex numbers that you will use in code is predefined. It's there, 1, 2, 3, 4, 5, like an integer. Here are all the complex numbers. And you have values for each of them. That's why they are final. But hang on. If that is the case, how do I add? How do I plus two numbers, right? So it is this set of predefined objects with values. I send it over as I have a given number, I add another number to it, and I return the answer of that complex. Okay, so this is somewhat strange. And when we get to section 3.3, you will see why are they doing it this way. Because if you have integers, you sort of, if you think about it carefully, you somewhat have the same thing. But okay, this is how it's implemented. That is what I want you to have a look at. So, how would the client code call this? Well, you would declare a complex number, and now you can new it. And now be very careful. Now I'm copying that reference for Z0. Yes, so I have only one complex number at the moment, 1 plus I. I copy the reference. Then I do something which is very strange. I say that reference set times Z plus Z0. This is something called chaining. And chaining says, because the instance method returns a value, a reference, because the instance method returns a reference, I can feed that into the next instance method. It's a bit like Python. Okay, so I don't like code like this, which assumes an order of execution. So I would have done this so that I can see it's that times that, Z squared plus Z0. Okay, so add the brackets, it makes your code more readable. Okay. Okay. In returning an object, look at the code over here. This code to add two complex numbers is applied to an existing complex number. Z is my existing complex number. Then I'm saying take Z, times it with something else, which incidentally in this case also Z, doesn't matter. Yes, so I get that second number that I have to times it with, I get that N. But because I'm saying Z times, I know which object I'm working with, and I times it with my parameter, yes, and I can declare temporary variables and do the calculation, but then in order to return a variable of type complex, I have to a new complex. So I'm making a new object which contains the answer, and I'm returning it. Yes. So I am not changing these values. You see that? So what you have to ask yourself is, how will, if I did not have final there, if I had these new values, how would the code be different? Because this is somewhat strange and you have to get used to it. If this bothers you, play with it for a bit, see how it works, and then try to change it without that final and somehow returning Z again, because then these values have to go into Z. I can't see how it will work, but convince yourself. Okay. So that is chaining, creating and returning new values, final values. Okay, section 3.3, why are we doing it in this strange way? Okay, now, read. There's another application called the Mandelbrot set. You're all familiar with Mandelbrot sets? My, yes, die vraag vir Wikipedia. Okay? Go Google it. Go have a look on Wikipedia what exactly a Mandelbrot set is. Otherwise, I have to keep on explaining maths instead of explaining computer science. It's a bit, okay, let me say a few things and then you can go read up on it. And I'll assume by Friday's lecture, 8 o'clock in the engineering building, right? You do remember that. Okay? Juffrou Daly, stuur my een van die WhatsApp goedjies van jou uit oor die verskuiwing van die klits. Right. So Mandelbrot sets are interesting. It's a set, right? The set is something which contains things. So it's a set of numbers. However, it's not known whether a given number is in that set or not, which is strange, because if I have integers, if I have a set A equals 1, 2, 3, and you ask me, is 1 in the set, I can say, yippee, yeah, I can see it there. With Mandelbrot, a Mandelbrot set, it doesn't work that way. You have to calculate a hell of a lot of things using complex numbers. There is no equation that gives you the set of points. You have a long sequence that you have to calculate. And this is the thing, depending on whether that specific sequence converges or diverges, the starting point of the sequence, Z0, is in the set. If it converges, it's in the set. If it doesn't converge, it's not in the set. Okay. So that is what you need to know. So please go read Mandelbrot sets. I'll take questions on that Friday morning. Otherwise, I will see you, no, not otherwise, I will see you on Friday morning. Take questions on that. Thank you very much.